Tes. 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 Masuk ke. Tes.
Tadi aku
Check. Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good morning and best wishes to all of us. Welcome to today's public lecture on the main topic, Protecting Precious Water Resource, in collaboration of Biology Department of Science and Mathematics Faculty and Cluster of Paleontology or Jepang. My name is Habibah Ayu and I'll be your master ceremony for this event. Before we get started, I would like to extend a warm welcome to your Honorable Professor Triratnaningsih Suprabhawati, MPPSC, as the founder of the Cluster for Paleontology or Jepang, your Honorable Professor Dr. Sabto Purnomo-Putro, MSc, PhD, as the head of Biology Department of Science and Mathematics Faculty, and your Honorable Professor Henk as our distinguished speakers who have graciously agreed to share his expertise and knowledge with us today. And last, our audience in today's public lecture. For the schedule of today's lecture, here's what we have planned. 9 until 9:30 is opening by MC. 9:30 and 9:35 is taking picture for documentation. 9:55 until 12 is material presentation followed by Q&A and discussion session. 12 is closing by MC. Ladies and gentlemen, let's move on to the first agenda, which is the opening. Let us begin today's event with a prayer regarding to our respective belief and religions. The prayer begins. The prayer is concluded. Ladies and gentlemen, moving on to the next part of our lecture, we are pleased to introduce our moderator who will be guiding today's discussion. Our moderator today is Ma'am Nika Delita Cahyani, PhD. Ma'am Dita is a lecturer in Biology Department at Science and Mathematics Faculty with a PhD in Ecology and Evolutionary Biology from University of California. Her research has contributed extensively to marine biodiversity, DNA barcoding, and environmental science. Her expertise and passion make her an ideal guide for today's season. Please welcome our moderator, Ma'am Nika Delita Cahyani.
Okay, good morning, ladies and gentlemen, and all the students. Thank you for coming today. Today we are here to hear the talk on protecting precious water resource, a whole catchment approach by our distinguished speaker, Professor Henk. Before we start, I will read a very brief CV of Prof. Henk, or can I call you Prof. Henk? Thank you so much. So prior to his retirement in 2021, Prof. Henk was a senior principal research scientist at the Australian Nuclear Science and Technology Organization and director of environmental research. Prof. Henk's main interest was applying nuclear technique to better understand climate change on the past. He was an adjunct professor in the School of Culture, History and Language in Australian National University College of Asia and the Pacific. Prof. Henk was also appointed Royal Netherlands Academy of Art and Science visiting professor in 2011. And I think since 2019 until today, is it still, he has been a visiting professor at Postgraduate School of Diponegoro University or Sekolah Pasca Sarjana Undip, hosted by Prof. Triratnaningsih Suprabhawati. So without further ado, I will give the floor to Prof. Henk. So Prof. Henk, the time is yours. We have maybe around an hour presentation and then we will have a Q&A. Okay. So, Prof, the time is yours.
Okay. Well, it's great to be here, and I'm not sure what all the background is of all the students here, but my background originally is in physical geography. I did a lot of biology in my undergrad and also in my master's, but for my PhD I switched to physics, isotope physics, and that's where I got my degree from. So I actually spent some time at 2 different universities in the Netherlands. The first 7-8 years in Amsterdam, and I spent almost a year of that 7 years in Amsterdam also at the Netherlands Institute for Sea Research to get a different experience from university. So I went to a government institute to work there on sediments in the coast, and that's where I built up a background in sediments from the coastal zone, but also in sea level research. During my PhD, I had to switch to another university, which is also very exciting, because after 7 years, your university, I'm not saying it becomes boring, but you know everybody, and it becomes like your family, and it's not always very exciting. So a new university can be very exciting. This talk today is really focusing on the Samarang and the Demak region and what's happening in the catchment. And from a historical perspective, say the last 100 years, the last 50 years, and especially the last 30 years or so, since we have Google Earth, you can learn a lot from by looking at the whole catchment, what's happening, and looking at the catchment health. So I actually interrupted my career in Australia for a few years. I worked for the government, the federal government, for the Nuclear Science Agency, which is equivalent to Batam here in Indonesia. But for 2 years I worked for the Catchment Authority in Sydney, which opened up a new position for me to looking at climate variability and extreme events and the effect on the water resources in Sydney. Now Sydney is not a very big city, it's about 4.5–5 million people. But the climate is very variable, so drinking water is not always 100% available all the time. And when there is a lot of water, then we usually have a problem not with water quantity, but with water quality. And that's something that is not too different in the Samarang Demak region, really. Sometimes you have lack of water, sometimes you have too much water. So today it's really about the whole catchment approach, because what I hear about the plans for the Demak region and for Samarang, it's all about the urban area, the coastal area, because it's subsiding, there's coastal flooding, tidal flooding, and try to fix that. But we are forgetting what's happening in the rest of the catchment. The catchment is quite large because it goes all the way to Rawapening, to past Ambarawa, Salatiga. That's all part of the catchment that actually provides water to Demak and Samarang. So next slide. So this is just a picture, a general picture of a catchment, and at the top there you see the mountains, which is very similar to what you have here. You have the mountains in the upper catchment, and then the water flows with sediment to the middle catchment, where you have lots of agricultural activity. You even have, as you see at the top there, you have a dam, because there's a dam near Rawapening, which encloses the water, and there's water release for electricity, but also for irrigation of agriculture downstream from Rawapening. Then of course, as you go further down the catchment, you get to the coastal plain, And of course that's where the Semarang urban area is, and in the Demak region it's a transition from rice paddies to fish farms. And of course all these different land uses have different impacts, not only on the water quantity but also on the water quality. And once the water, the fresh water, finally makes it to the marine environment, then depending on the quality of the water, you might also have an effect on the marine environment. The marine environment is just as important, and people forget that because they think, oh, the marine environment that's important to us starts here at the coastline, which is mangrove, and then the mangrove protects us. But even a bit deeper at sea, there might be seagrass beds, which also protect the coast, but then they don't like a lot of sediment coming in and smothering the seagrass beds. So you have to be looking all the way, say, from 10 meters deep all the way to the mountains to get a big picture of what's going on. Now this is just an overview of your catchment. So on the right hand side, the high mountains, Mount Ungaran and surroundings in the Rawapeni area. It's partly urbanized because even maybe 30 years ago there were not many people living there, but now a lot of people live around the lake. So it's farming around the lake and also farming on the lower slopes of the mountains. So that farming increased quite a lot over the last 50 to 70 years. And of course, the middle catchment is the hilly bit with some of it is still forested, but it's partly urbanized and there's orchard farming along the river courses. And what you can see when you go there is there's lots of little dams that divert water to the fruit trees for the growing and production of fruit. Then you go to the lowland, and then you get to the Semarang, Demak area. Of course, in Semarang it's heavily urbanized. In the Demak area, it's a mixture of urbanized and lowland rice paddies. And then you almost get to sea level, and that's where you get the very intense urbanized and dense urban areas of Semarang. And there's also then the rice paddies changed to fish farming. So that was just a general scheme, and I think this is what's happening in the catchment. So at the top there you get a big dam, keeping a lot of water into Rawapeni and releasing it at a steady stream for electricity production. But it also captures sediment. So instead of the sediment escaping from, and the nutrients escaping from Rawapeni, it's actually trapped because you don't want the electricity generators to get clogged with sediment, so they actually stay within the lake. So the lake is getting shallower and shallower and also more eutrophic. Now in the middle catchment, there's lots of little dams and structures that divert water for irrigation, and they also trap a little bit of sediment all the way to the junction between where the rice paddies stop and the fish farming starts. So with all this trapping of the sediments, as you can see, there's no yellow dots in the last section near the coast. So that doesn't receive any sediment to build it up in a vertical way. And that's a problem, because if you take away all the structures that men built, all these dams, and especially the big dam, then of course you get more sediment supply to the coastal zone and you build it up slowly. So it's not keeping up with predicted sea level change. The second problem in that coastal zone is, of course, that you all hear about, is the extraction of groundwater, which lowers the groundwater table and also makes the land sink. So these two processes have a very severe effect on the coastal zone. And That's why there is a lot of land subsidence in Semarang and in the Demak region. I'll come back to that later, because the rate of land subsidence versus sea level rise, that is very stunning. So there's two things that I want to discuss a bit later. So the first issue that I noticed in the Demak as well as the Semarang region is the rapid discharge of excess water. Now, this is a relic from the colonial era. So the Dutch people that built these canals, they're very good in building canals, because that's what they do in Malanda as well. And that is to discharge the water as quickly as possible and protect all the infrastructure like Semarang City and coastal regions. Now, if you do that, you make well, you can see them in Semarang. They are actually concrete channels that discharge the water straight to sea. So there's a loss of opportunity to feed the floodplains next to it with sediment. And you also increase the turbidity in the marine environment, which has a negative impact on the marine habitat. So all of a sudden, instead of putting a little bit of sediment on the floodplains, all that sediment goes out to the marine environment and gets deposited very quickly near the mouth of the canals entering the Java Sea. So that's where, if there is any healthy habitat, then it gets smothered by this sediment very quickly. So this is the example of the canals that have been there for a long time. And of course, these are embankments on both sides. And the whole purpose of it is to protect the urban areas on both sides and get rid of the water in the wet season as quickly as possible. So as I said, it starves the floodplain of sediment, but it also it misses the opportunity to give the coastal floodplain, the aquifers, the groundwater, to recharge with fresh water. This is all precious fresh water going out to sea, and fresh water is very precious for a whole range of purposes, for industry, for urban areas, for agriculture, and you just pump it out to sea as quickly as possible because it might damage the urban infrastructure. And it doesn't recharge the underground freshwater aquifer. This is the same in the Demak region, so you can see the normal winding rivers in a landscape have been changed completely in straight canals to discharge the water. And of course, in the rice paddy area, there is the opportunity to discharge water towards the rice paddies, but towards the sea, there is no much opportunity to supply fresh water and sediments to the fish farms. So this loss of contact between the major fluvial discharge channels and the floodplain. So there's the two problems that it causes is that it's the floodplain is starved from sediment supply, and that is during the wet season mainly, and also the multiple dams in the middle and upper catchment, they trap the sediment from the upper catchment anyway, and that's the two problems. So the solution might well be that you create more space. Now that's a bit difficult in the Semarang urban area. You cannot let the floodwaters deposit more sediment in the middle of the city, but you have to dedicate certain areas where you can actually have that happening. So give the floodwater by giving back to nature. These spaces that will act as sediment traps and might replenish coastal aquifers. It's also larger water capture dams in the middle catchment might act as replacement of water extraction in the coastal stream. And that's something that's happening in Semarang very slowly. One of the reservoirs was only opened in the 1980s, and that actually had a dual purpose. It was there for capture precious fresh water and also to prevent some of the flooding. But that dam, which is in the southwest of Semarang, only has an effect on, of course, on the southwest and the west of Semarang. Okay. So this is how it works when you actually dig back to nature. So the current situation, you have the river or the sea, you've got a sandy beach, you've got the clayey foreland, and on top of that you have lots of development. So if you dig out some large areas that you give back to nature and you make forest development or mangrove development and marshland, and you use that as a safety area when the flood happens, then you might mitigate flooding of these areas. And that's not only in the Demak area, but also this could work in the Semarang area. But it has to be a lot of planning, and of course these precious lands that you give back to nature can no longer be used for development. So it's an economic decision that you have to make of further development and ignoring the flooding and the tidal flooding as well. That is threatening the economic development. Or you invest on something like giving back to nature, and then you have a better model of dealing with the problem. The Dutch people in the Netherlands did the same thing. They did canals and they tried to get rid of the water as quickly as possible because everybody is afraid of the water. They don't want the water, they want it out at sea as quickly as possible. And that was a 19th and 20th century thinking. So this new thinking of giving back to nature and let nature help you manage the landscape is quite new. That's something of the last 20, 30 years. And it was introduced, I think, in the 1980s and 1990s. But then it took another 10, 15 years to implement and to start assigning precious landscape back to nature rather than development in an economic sense. And this is what it would look like. So instead of trying to straighten the river to the sea and get rid of the water as quickly as possible, because that's what the Dutch people did in the 19th and 20th century. They thought these meanders of the river that slows the river down. That's the natural process. So they can actually have deposition of sediments at either side of the river, but it's a very slow river. Now, if you cut it off, you cut a canal through here and then straight there, and then you cut out a couple of these bends, the increase of the speed of the water going to sea increases because it's a shorter distance to the sea. And that's what they liked. But then they forgot that when there is a flood, it becomes a problem because it's very fast flowing water all of a sudden, and there is no extra space on either side of the river to deal with that. So now they're going back to a model where meanders are okay, but also that there would be openings in the levees next to the river, that they have these basins where excess water can flow into and then fill up. And that might only happen once or twice in 10 years, that excess water fills this, but it protects precious developments that are happening elsewhere, economic developments, urban areas. And this model is now being seen as almost landscape architecture to deal with that problem of flooding. So this area cannot be used for anything else in the economic sense, but in the socio-economic sense, this is a big recreation area as well. Like most of the time it's nature, people can go there, walk, cycle. If there is lots of water, they can go boating or sailing or swimming. So it's not a lost opportunity. It's actually very good for people to have those areas near urban centres. And it was a very good plan. And initially they said it's going to be too expensive. But the alternative was to build the levees up to, say, from 5 metres high. So you get a 5 metre high flood with the river up to 15 metres. Of course, these levees, like in Samara, where you have the channels, these levees are quite low. So you can imagine if the decision is made to make them 15 metres high, that is a lot of cost to the local government. And you might protect the city more if it's 15 metres high, but if the flood is 16 metres, and the levee fails, then you have all of a sudden a lot of water flowing into Samara very rapidly. So that's a very dangerous situation. So instead of building up a levee, they actually cut holes in it and have this basin for the excess water, which is a very novel plan. And I think that's, I think it might work here as well, because the digging of the hole is probably less expensive than all the damage that you can potentially do to the urban areas. Now, as you can see, this is a map of land subsidence, and the darker the colour, the more land subsidence there is. And then, of course, it's the highest in that coastal zone in the transition from the rice paddies to the fish farms. So very close to the seafront, to the coast, a little bit inland. And of course that's where the extraction is of fresh water for domestic use, agricultural use and industrial use. But you know, the landscape is sinking quite dramatically. So this is the picture of just outside Samara in the northeast, on the way to Demak. That is the region that is under threat at the moment of coastal flooding. So the coastal reef erosion, you can see the loss of mangrove cover. So the first thing that disappears is the narrow strip. On the left-hand side, you can see still a bit of green right on the seafront. That's the narrow strip of mangrove. In the next photo, which is about 5 years later, most of that has disappeared, and then the more recent photos, there's only mangrove islands further back. There's a loss of mangrove covers over the last 100 years. If you look at old maps of the Samara and Demak region, you can actually see that the coastline was further out. There was a lot more fish farming, and the mangrove was also further out. So there's a change of the coastline shape. I will discuss that in a minute. There's the introduction of man-made structures that influence the wave action, which has an effect on coastal erosion. Of course, there's subsidence, and there's the sediment starvation. The sediment starvation I discussed in the early part of my talk. So the sediments that normally come from the mountains no longer make it to the coastal zone. So there's this imbalance of sedimentation in the coastal zone. Now, this is a model that some Indian colleagues did, and it's different types of hydrographic conditions on the coast. This is where there's major drift, so the major current on the coast is along the beach. That is, there could be a little bit of beach erosion. If you have straight waves coming in at the coast, between two rocky outcrops, then you actually build up the coast. If you have an angle of the waves, then you get a little bit of coastal erosion. But the most unstable situation is if you have an irregular coastline and you have waves coming in and the onshore current is along the coastline, then you get, it's a very unstable coast. And I will show you what happened to the coastline of the last 100 years in the Samara and Demak area with a couple of images now, and you will see that the situation went from minor drift, minor accumulation, sometimes erosion, to very unstable. So this is the region, Samara in the middle there, the muck a little bit to the right. It's a bit difficult to see maybe, but the thick line is the current coastline, which is a bit erratic in the Samara area, and then all the way to north of the Mac, there's also a bit of an irregular coastline. When you zoom in, it's more apparent. So in blue here, the very toned, this is the old coastline. So it's a smooth line. So this the green line is what the coast looked like in 1896. Very smooth. So it's a semi-stable, sometimes accumulating, sometimes eroding coastline. What we have now in the 2000s is this coastline. Alright, so this is the red line that I tried to draw and mimic that coastline. And of course that irregular coastline is actually very unstable. So when waves hit that, then there's lots of refraction of the waves, and refraction of waves that's actually eroding the coastal wave. So it went from a stable situation to an unstable situation. And that's just the hydrographics of the marine system. But when you can think by yourself what causes all these irregularities. Well, here it's coastal erosion, but here it's definitely development. As you can see here that the coastline is actually expanded into seawards for the port of Samara development. So these irregular man-made structures actually change the hydrographics. That also means that you probably have to dredge out the harbour in Samara a little bit more often because sediments get trapped inside, and then other regions it's heavy erosion. Okay, so now something about the water quantity and quality. Dry season versus wet season. So it's high water supply in a wet season, but it's usually low quality. And in the dry season, you might have the opposite. So what we're going to look at a little bit now is the natural catchment versus the development catchment, and also the Jati Banana Reservoir, which I alluded to earlier, that would be hopefully more to come, because I think that is one start of dealing with the problem of over-extraction of water in the coastal zone. That was just the coastline that we discussed, and natural catchments versus urbanized catchments. And of course, this is the population graph for Samara for the last 80 years or so, 1950. There weren't many people in Samara, maybe 300,000 people. And now we are approaching rapidly 2 million people in the greater Samara urban area. And of course that has a problem. So if the planning doesn't keep up to make it a sustainable city, then you run into trouble. It's interesting to see that sudden increase in the 1970s to 1985 or so, the sudden increase in population by percentage. So that's, maybe lots of people have babies in Samara. Now, as I said, in the upper catchment, that is where all the good things should come from. Lots of water from Danau Rawapening in the middle there. So this is a picture of maybe 30, 40 years ago. The lake was in reasonable condition. But if you look at Ambarwa and Salatiga here, there's lots of agricultural and bushland cover around in the catchments around the lake. If you compare that with more recent picture, the next one, then all of a sudden you can see that Salatiga has grown quite big. Ambawada links up along the road past Rawapanin, so it becomes a semi-urbanized area. And if you urbanize the catchment, what you do is you change the hydrology of the system. All these park roofs of houses, they are not absorbing any rain. They just let the rain fall off. It falls next to the house, and of course next to the house is more concrete to keep your feet dry. And then of course where does that water go? So that water becomes an erosional problem, and nutrients and sediments all flow into Rawapanin, and that of course then causes eutrophication. That might not be the only issue for Rawapanin, but a very quick urbanization in 30-40 years and not being able to let that water soak into the aquifers around the lake is a bit of a problem. All right. And if you look at the middle catchment, this is southeast of Demak. So you can see this is an old picture as well, maybe 30 years ago. This is the major rivers going to Demak. You can see under Pravata there's lots of green cover of the hills, and here as well there's lots of forest cover. And if you then look at the next picture, that forest cover has been cleared, and here as well, and there's a lot more agriculture around this area. So this is probably a forested area which is used to clear for forestation, for timber. And so there's even in the middle catchment there is a fair change in land use. Now this is just a picture of how quick Semarang has been growing. This is 1984. The yellow line is roughly the eastern edge of the development. So we go to 1984. Next one, 1990. You can see along the major roads, especially in the north east corner there, the top, there is extra development. And if you keep an eye out on that, where the yellow line starts at the top there, that's where the erosion of the area further north is actually starting in a couple of slides. So the next slide. So here you can already see just above that yellow line, there's more development there underneath the yellow line in the north. Big industrial areas and expansion of the port, and then you start nicking into that fragile coastline with very little mangrove. Once you do that, you've triggered a process that you can't stop. So nature will take its course and will erode the rest of the mangrove away. So the next slide, this is 2019 now. You can see there's a tiny little bits of mangrove islands left on top of the yellow line. But you can also see that in total, the urban area, there's not much left between South Semarang, Ungaran and Ambawada. It's all one big development, and also it's gone wildly to the east here. So this is not good if you want to manage your flood and your health of your catchment. So you have to do something. So this is an example of a purely natural situation. So this is the Lawrence National Park in southeast Papua. This is the situation in 1984. There's no development. There's no pressure from clearance of the upper catchment. This is only a picture of the coastal zone. So this is massive mangroves and then fresh water swamps. But if you compare that with the next one, 2017, there's no change to the coastline whatsoever. While in that period of 30 years, we know that sea level has risen by maybe 1.5 centimeters. But here is no land substance. So the national system takes care of itself and it's a very stable coastline. What might happen is that these rivers, when they meander, they might actually leak into another one, and the sediment supply goes from here to here. But these areas next to the river, they all receive sediments from the rivers and the upland catchment. And the whole system is in balance. Now, to change back in the Samaran region to something natural like this is impossible, but we can learn from this that this is a stable coastline. So what do you need to do to make the coastline more stable? Now, this is something that the local government, even the Central Java government, came up with the UN. It's called the UN Habitat Report 2022. And you can see that they are doing a lot of planning on how to make it more sustainable, the whole Samaran region. But what they give back to nature, or what they keep as nature, is the mangrove restoration area that is not far from the airport. But then next to it, they're planning a port and industry. So if you do both in the same area, then you might actually not gain much by leaving the mangrove restoration area as a natural process. The same thing at the Polder Kali Samaran is an area where they try to replenish with new sediments. But here are the reservoirs to keep the water in. And as I said, that's probably benefiting the western part of Samaran, but in the eastern part there's no such thing, so extraction of groundwater is still going to be a problem probably. And as I said earlier, in orange is the current coastline, and then all the black lines is the extension of the coastline in new developments. And I think that will still be irregular and might still cause some problems. And it says building with nature towards the muck, but that's almost an afterthought, because if you see how much development is going on just across the border into the Samaran proper region, into the muck, then of course you can see that one has a big influence on the other. It's a district boundary, it's not an actual boundary, so you can't say, well, we're doing this in Samaran and we don't know what's going to happen in the Demak region. Alright. So at the moment, I feel like all of the talk is about sea level rise, coastal erosion, water extraction, and that is just one problem. So tackling one problem won't solve the current problems in the coastal zone, because you have to look at that whole catchment. Why is it not more sediment coming to the coastal zone? The challenges really are, we don't know what future climate change is going to do when it comes to the intensity of the wet season. Is the dry season going to be longer, which basically means that you have to extract more groundwater? Or there might be a possibility that the wet season is going to be more intense and more pulse-like, with greater chance of flooding. So these are possible changes to the wet-dry season intensity. And we can learn from Sydney in that sense. Because in Sydney, we did the climate modelling under climate change scenarios maybe 25 years ago, and there was a prediction that summer rain, the total rain would be the same, but it would come in very intense rainfall events. And intense rainfall events are really good for flooding. So over the last 5 years or so, which is about 20 years after the modelling, things came true. So we had quite a big flooding in Sydney with lots of damage to houses, lots of, lives lost as well, but economic loss was quite big. And we knew about this 20 years ago. It's just that the planners, they didn't believe the modeling. So they still kept planning in the wrong areas. So if you have climate modelers that say, hey, rainfall will be more intense and will cause flooding with the current infrastructure, we have to do something about that. So the floodplains around Sydney should be left alone. Where I live, they are largely undeveloped, but it's attractive for developers because it's flat land, it's sandy, it's fantastic to build on, it's cheap, and so they want it open for development. But of course, the more the scientists actually say no, don't do that because it will be a massive risk to the population if you do that. You will actually put more people at risk if you start developing them. So, and we already know that the predictions of that little bit of 1.5 degrees or 1 degree of warming has increased the intensity of the rainfall around Sydney. So, number 2, sea level rise. Well, the predicted sea level rise for the Samarang area is not spectacular. So they predict in a moderate scenario maybe 20 centimeters, and in a more drastic, very high, like a more intense scenario, maybe 25 centimeters. So sea level rise is something you have to take into consideration for the rest of the coastline, which is not prone to land subsidence. So outside, further west, from Semarang to Cirebon, you might want to look at sea level rise and what that does to the coastline. But around Semarang and Demak, of course, if you look at land subsidence, it's 3.3 meters. It's a moderate scenario, and an extreme scenario is 5 meters of subsidence. So that's a far bigger problem. So to start worrying about, what should we do about sea level rise? We should build a seawall to keep the sea out. But if you ignore what land subsidence is doing to the landscape, to the city, then you're putting your eggs in the wrong basket. And as I said, the urbanization of the area, if it's low and high, if you have high urbanization and also the scenario of 5 meters of subsidence, then of course you create a nightmare scenario. So unless groundwater extraction is managed, it's a slow onset of a disaster, really. So that's what you're facing. So instead of all this economic investment in the region, which is good for everybody, but you might find yourself in an unlivable city in 20, 30 years' time. Now, in a graphic, it looks a bit like this. So you've got the natural water cycle, you've got the rainfall in the upper catchment, you've got infiltration in the soils of the coastal region, the groundwater. So you have high groundwater flow, you have good filtering capacity in the coastal zone. The urban cycle, water cycle, is quite different. So you have a lot less infiltration into the subsoil because it runoffs straight to sea, all that precious fresh water. Also, there's a lot more pollutants that go with it from the urban area. And if you have a more sustainable urban water cycle, then you create these wetlands, these areas where the rivers can deposit sediment and store water during flood events. That is actually, that does both wonders for much better infiltration, the recharge of the aquifers, and so you build up the resource for the dry that if you still want it, but it's a much healthier option towards a more sustainable water cycle. So at the moment you're still in the middle, and hopefully you can move to the right picture. So this is something that my colleagues at the nuclear organization in Jakarta have worked on, they actually worked on trying to fingerprint where the sediments come from in the catchment. So which land use produces the most sediment that makes it to the coastal zone. And so you put a fingerprint in by looking at radioactive isotopes and stable isotopes and also chemical elements. And then you come up with a model for different land uses. So these are the different types of land uses like fish farms, rice paddies, forest, and other fruit trees, that sort of stuff. And then by looking at the sediments at the bottom of the catchment in the coastal zone, you can then get a diagram on low flow, low river flow, during the dry and high river flow, and then you know exactly what the percentage of these landscape land uses is with contribution to the sediments. So if you want to stop excess sediments from one region because it's not healthy, for example, the forestry might be not the way that sediment you want to end up in the rice paddies, then you can actually change the land use a little bit to change that mix. Okay, that was the end of my talk. Thank you very much.
Thank you so much, Prof. Henk. So we now going to open the Q&A session. So if some of you have a question, you can raise your hand, you can ask a question. You can ask a question using English or Bahasa. Okay? So who want to start with a question? Please, don't be shy. Come on in. I think you already have one. Okay, one question here. Who else? Because this is really interesting. Dr. Henk, Prof. Henk tell the whole presentation about Semarang. So this is very close to us. So I'm sure that all of you have a lot of questions because I do. I have a lot of questions, so I will be a student after this. But if other than you have a question, please raise your hand because there might be a good idea about your research, your next research, or just how you understand our ecosystem in Semarang. Okay, maybe we start with the first question. Do we have another? No?
Okay, thank you for the opportunity. Maybe I have one question, sir, about, I want to ask, usually every year there's a flood in Semarang, and this happens because, the land in Semarang is getting down every year, and then sea levels are going up. And I wanted to ask, can we solve this problem with maybe building a dam and then make a pump water system? I heard that in Holland they was already used for many times years ago to make the, like a water pump system. Maybe what if the Semarang use a system like that? Can it solve the problem, sir? Thank you.
That is a very good question. What the Dutch people had problems like this for a long time. They had land subsidence caused by human activity, draining the land and then oxidizing of the sediments and then it would sink. The problem that Semarang has is that it's a very recent problem. In Belanda, they caused the problem maybe 1,000 years ago when they started using the coastal slopes for agriculture. And then they tried to fix it by building dikes. So these are not concrete, not beton, but it's man-made mounds like levees to keep the water out. But to keep the water out is also to pump the water out of your area where you live into the sea. And I think that's where, that was much later, maybe 500-600 years ago, that's when they started pumping the water. And of course, about in the 1600s, like 400 years ago, they invented the windmill to pump the water from low-lying areas into a canal, and then it would be discharged to the sea. They've been building that for hundreds of years, and then of course in the 19th century they replaced the windmills with steam engines, and later by diesel engines to pump the water. It's a very expensive infrastructure. So, and that is just to fix the problems that we caused maybe 1,000 years ago. So it took a lot of time and money to fix it. Now, in the beginning, when there was no windmills and there was no way of pumping, people still built dikes, and it was just a communal thing that people would, the community would come together and build it and maintain it to keep themselves safe from the sea. So there's a long history. Of course, with the population also started exploding from not like the last 50 or 100 years, but maybe as much as by 50% in Belanda in the 16th century, which also causes these problems. Of course you can build dikes here, but then that will take many years. It will take up a lot of resources. So it's probably easier to solve the problem of land subsidence, which I indicated is water extraction, to fix that than to try and fix the cause rather than the problem. Right? So when I say that, is the cause is water extraction, and the water is coastal flooding. But if you build a dike, you fix the coastal flooding, but you still haven't done anything about the cause. Right? It's like when you have a headache, you take a pill for your headache, but you don't know why you have a headache. So you want to know why you have a headache, which is, in this case, water extraction. So storing more water in the catchment, in the forested hills around Samara, with more dams, that will help greatly. There's hardly any water extraction in the coastal zone in Sydney, a city of 4.5 million people, because we have massive water dams in the forest catchments to the west of the city and to the south of the city and to the north of the city. We have maybe a total of 15 dams. One of them is about 14 kilometers long and 100 meters deep at the dam. That has drinking water in it for 4 million people for more than 2 years. If there's no rain in 2 years, we still have drinking water. So we don't need to extract. We also have desalination plant in Sydney, just in case. That's very expensive, and I know that in Samara you have desalination plant as well, or in Demak. But it's very expensive, so building a dam for drinking water and water filtration plant is still cheaper probably. And also desalination is very energy intensive, so it's not very greenhouse friendly to do desalination if you don't have alternative power sources like wind or sun. But I'm surprised that with water pumping, for example, and if you want to do it on a small scale, like you want to protect your village and you have a protective wall around your village, like an earthen wall, and you use alternative energy like solar or wind to pump the water out of your urban area. That could work. It's just that the most affected region, just to the northeast of Samara, all the population lives along these roads that are very narrow and that goes on for kilometers and kilometers. So it's very difficult to protect these people. If they all live in a circle of 200 meters, very densely populated, it's easier to protect. So it's the way you build villages as well that you might easily solve it.
Any other question? Okay. Can you go to the front a bit?
Alright, good morning, Sir Henk. Thank you for the opportunity today. And however, I find your research really fascinating. And however, it appears that I have some questions for you. So firstly, there's been like water dredging around in Semarang in Demak, and there has been some kind of what you call it, rebuilding of new canals around Demak and Semarang. And my question is, are those those anthropological process hinders and interrupts the water quality around it? And does it really affect the local activities overall? And secondly, I have some questions. I have two questions. Which one is better, finding new catchments or preserving pre-existing ones? Thank you.
So if I understand your first question right about drinking water quality, the reason why people use groundwater in general is because the water is already filtered by the biological microbiology processes within the aquifer. So the quality of the groundwater is better than the surface water. It's just that when you build reservoirs in the upper catchment, which are undeveloped and maybe forested, then that water quality, that surface water quality within the dam is actually also very good. You just have to do some filtration, but not a lot. So for groundwater, depending on the depth, it can be reasonable quality, but depending on the activity at the surface and when the water penetrates into the aquifer, it could be contaminated as well. I mean, the whole many millions of people in Europe died from contaminated groundwater in the last 500 years, and that was the biggest problem until they started diverting the wastewater from urban areas away from the groundwater people were drinking. Of course, that's another problem that you might have, that there is no separation, good separation from sewage water and surface water, and of course that will affect the quality of the drinking water in the aquifer. That's why I'm more inclined to suggest that the big reservoirs in the mountains are better because there won't be as much influence of wastewater mixing with clean water. So that's probably with the water quality. And the other question. So the question is, do we preserve the existing one or do we build a better one? It depends on which part of the catchment. I think the middle catchment and the upper catchment we cannot do much about. But the lower catchment, the urbanized area, when I showed the picture of the UN plan for the Greater Sahara region, there is very little that says to me this is a really good plan for floods, to mitigate floods, or to even replenish the aquifers. It's all about, okay, we have a mangrove area here we should preserve, which is coastal protection, but that region is not very helpful for preventing floods. And flooding is the bigger problem than the coastal erosion in Sahara. So, although, you know, one causes the other, but I think you really need to think about the excess water during the wet season. Where does it go? And if you make it a bit more natural, with space for the rivers to go somewhere else and deposit sediment and store water temporarily, that would be a better. So I would re-engineer the catchment to protect this very expensive infrastructure that they're building.
Still have any question? Is there any other question? Please raise your hand if you have any questions. Jangan malu-malu. Go ahead.
So any other question? Okay, while waiting, I have a question about when we talk about the land subsidence, it is meaning by because of the water is rising, or is it because the land is sinking? Which one it is when we talk about the land?
So all the sediments in the coastal zone, so maybe from the mangrove, which is zero, to inland, to the end of the fish farms, and then the rice paddies, that's all the coastal plain, maybe 5 to 10 kilometers. And that's where the water extraction happens. And what you do is you pump the water out, and then the water pressure of the aquifer, actually, there's space between the sediment particles. And if you suck the water out, then you compact the sediment. And that leads to land subsidence. It's a bit like if you have a pack at home of your clothes, and you put the vacuum cleaner on top of it, and you suck the air out, then you end up, instead of this thick, you end up with this thick, and that is land subsidence. And that is, depending on the type of sediment, it's sometimes it's very difficult to reverse, you see, because if it's a very clayey sediment with sand, then of course the clays don't, you can't re-wet them quite easily. So that replenishing of the catchment with water from the upper middle catchment and the upper catchment is very important. We have the same thing. We have mega droughts in Australia, and during flooding periods, which are not very often, most of the water disappears towards the sea. But there are clever farmers that try to divert much water on their property to store the water underground. And their properties usually do much better in production during the dry period because they have a better storage, a backup of that water. And that's what's happening here. It's just that in Australia, in the coastal zone, people do extract water, but they try to discourage that because of the same problems. The vegetation dries up much quicker at the top, becomes more susceptible to fire, and fire is also a big threat to infrastructure in Australia.
Any other question?
Any other question? Yeah, because we do have this problem in Samara. That's why I asked, because sometimes when we talk about the water, the land subsidence, we thinking about, oh, maybe the seawater level is rising because we count our land based on the sea level. So, but turn out it's also because it is actually sinking because all the water inside of the sediment is being, extracted out from the sediment. So that's also another problem that we have to think about. When you have a very compact sediment, I think that's also, trigger the flood as well. So if you have another question that you might be still. Okay, we have one. Is there any other question? No? Okay, please. Silakan.
Okay, thank you, Prof. Henk. My name is Abdul. I'm currently a student of Master Biology program. Firstly, I would like to say thank you so much for your concern towards Semarang flood problems, because I live in Semarang for my whole life, and I know how it feels to you wake up in the morning and your home is flooded like that. So my first question is, we know that our river in Semarang is kind of like straight to the seabed. So let's say our government has the funding and want to alter the river to be more natural. Is there any model from other countries which have already done to change the river, and is it possible to do it in Semarang? And the other question is, when I see your presentation about the future sustainability of urban water cycle, we need to build kind of wetlands so we can act as filtration for the water. What kind of wetlands we can build in Semarang? Because when I think wetlands, it may be like rice field, but I don't think it's the right one, because, well, it's kind of like not organics. Maybe this chemical will be deposits in there. Thank you.
Well, there are examples of connecting rivers with different rivers in the Netherlands as well, where they want more water through the port of Rotterdam to keep the port open, and then less water somewhere else. So you can dig canals in between and then divert the water away from the center of Semarang. That would be a possibility. It's just that it's so densely urbanized already that it's difficult to do that without massive disruption to neighborhoods. It's like if you want to build a whole new road through the city of Semarang, that's also difficult because there's lots of people living on the trajectory of a new road. So that's a canal is just as difficult to do. The other one is actually biologically it's interesting. That ecosystem that I was talking about, like a freshwater swamp where you store water, that doesn't exist any longer because the human history of the Semarang region already changed that into rice cultivation a long time ago. So that transition from the hills to the coastal zone to the mangrove, that is a very cultural landscape. It's not a natural landscape. If you look at that picture that I showed you from the south coast of Papua, there is a massive transition zone between freshwater swamps and saltwater swamps, which is then, of course, mangrove. That ecosystem no longer exists anywhere here in the region. So you have to think about using paleontechnology, what Professor Klee does, to see if we can reconstruct what an ecosystem would look like in a freshwater swamp. And that freshwater swamp, it could be an eco park as well. You know, it doesn't have, it has a lot of economic value in that sense, socio-economic value, because it's not lost. Lots of people that have dollar signs in their eyes, they think, oh no, that's too expensive, you should do it. No. You protect very expensive infrastructure by doing it, but you create something that is actually very valuable to people to make them happy. And you're basically restoring part of nature that was lost. So I think it's a win-win situation that you can do something like that. And even if you do it on a test model in one small part of the Tamak region first to see if it works, that would be great. Yeah. And in the example of the Netherlands, where they created those new lakes and swampy areas to store extra water, these are immensely popular with people, and they really like it. They see it as, oh, we're going on an eco trip. So, yeah. All right.
Any other question from the students? No? Okay, while waiting, I have another question before I give it to Prof. Tri. I'm just curious about what we need to do the mangrove replantation. But the problems here sometimes is the wave is really strong, so the mangrove is not really survive. So is there any idea on how we can do that? Like, is there a way before we replant, there's a plan to do something to make sure that the wave is not that hard first, and then we replant the mangrove? Is there any, things to do?
Okay, so we actually had a meeting yesterday in the Tamak region and the regional office, and they are actually coming up with solutions already. They have these structures, like a circular beton. They stack the 3 at the bottom, 2 at the top, and then 1 at the top, like a little pyramid, and then that creates a barrier from the wave action, and it also allows sediments to accumulate behind the structure. And I think they said it's more effective than bamboo structures. And then of course, once that these concrete structures are working, then you can plant new mangrove behind it and then protect it. As I said, the sea level is, personally I think it's a small part of the problem. Right? It's the wave action, but the land subsidence, the combination of those two, and the change shape of the coastline, that is causing the massive problems. What the Dutch people would do is they probably would build a whole new ecosystem with a big barrier, with a porous barrier where you can get water in, but not a lot of wave action, and then accumulate more sediments. But the sediment supply to that part of the coast is also, there's not much sediment coming into that system, so it's all the existing sediment that you redistribute. So that's another problem. And I'm not claiming that I have all the answers for Savannah. I just want to have a discussion about what is possible. And I can see the same issues in Australia. People, often the investors, they just want a return for their money. And so the nature is always second in their thoughts. The first thought is to make a profit and to develop, and not think about the problems that they might cause 10 years, 20 years from now.
Any other question?
Okay, please.
Okay, thank you for the opportunity to I ask. And let me introduce myself. I'm Irma from Biology Department. I will ask you for about the good dam in Semarang. As we know, Semarang have a lot of population in the lower area, like near to Marina and like the others, and it tries to complicated regulation if we build them in the lower area, like how we move people into another area, like they already live there for some years, and also how to change or claim the out of the field from the field owned by citizens become the government field to build the dam. Where if we instead of build them in the lower, we better build the dam in the upper area of Semarang, like in the Ungaran or near to Rawapening, because like if we build them in the lower area of Semarang, it drives to the dam become have polluted water, and also it will pollute the like near to dam, and then it cause as you tell before, we can like people consume contaminated water, and if we build them in the upper area, we have better quality of water in the dam. So yeah, and also the debit of the water in Bandungan and Ungaran near to Rawapening, it also cause the suddenly fall in the upper area. So I prefer to build them in the upper Semarang, like that. So how your POV of this idea of this suggestion for me, sir, is enough. Thank you.
Okay, it's a good question, and I think there's a lot of the poor people living in the lowest areas and the most affected areas by coastal inundation. So to do nothing is not an option. To build a seawall is not going to fix the problem either, because the seawall might protect from coastal inundation, but during a wet period, when a lot of fresh water runs off and into some other area, then of course you still get the flooding. So the number one priority is really stopping extraction of water from the coastal aquifers. If you want to have a direct effect on the amount of water getting into the coastal zone from the upper catchment, then you have to build dams, more water retention dams, flood mitigation dams they're called, in the upper catchment, in the Ungaran area and there, because you shouldn't build them in the low area, build them in the highest area, and even if it moderates the pulse of the flow. If there's no dam, you get a sudden flood, which comes up very quickly, but it drops very quickly as well. So that's a very frightening effect. If you have slowing down of that pulse by flood mitigation dams in the upper catchment in the hills, then you might actually dampen the flood height. And also when it stops raining, then you can actually release water to flush out the system. Because during the dry, these systems, these canals are horrible places because of the accumulation of waste and there's no water to flush it out. So you can use it for both keeping the the system cleaner, but also to the pulse height. The pulse height is the problem. That's where most people get killed. I remember from Jakarta, for example, that some of the smaller dams near Jakarta failed, and then all of a sudden this high flood came through the neighborhood and killed all the people. The slow inundation on the coast in the poor areas of Jakarta is terrible, but it doesn't kill people. It might make them sick, but it doesn't kill people. So you have to be really careful, try to mitigate the flood level, the sudden flood. On television we saw the horrible news in Spain where lots of people died in Valencia. It was unimaginable how quick those came. They all said, oh, we weren't warned by the government, what happened? But it happened so quick, even if they were warned, they would probably be caught out. So, yeah, that's terrible. That's what you want to slow down the system.
Thank you, Prof. Okay, any other question? Okay, before I ask Prof. Manning, I have last question, and I think most of the students would interested to hear this. You said that you have interest in applying nuclear technique with the climate change. You have one of those examples in your presentation. Can you elaborate more what type of research that we can do to combine both topics? Thank you.
So a lot of my work over the last 30 years or so was to do with how systems accumulate sediment. And in the macro system we can actually measure by looking at the radioactive isotopes how quickly the sediment accumulates. And if we then know what the sediment sea level rise is, or even the subsidence, then we can do a calculation to see if the system is stable. If you don't know how quickly the sediment is accumulating, then you don't know if it's going to cope with sea level or subsidence. The first study I ever did was a situation in the Netherlands where there was subsidence. Sea level rise was not big, but subsidence was the problem. And when we measured the sedimentation rate using isotopes that are naturally occurring, you can actually measure the concentration of the isotope at the top, and then you measure it down the sediment column, and then you find a decline in the isotope activity, and then you calculate in centimeters per year how quickly it accumulates. And we do that for a lot of people that study mangroves. But it also provides the same technique if you want to know how quickly Ramapani is silting up. The accumulation rate of the bottom sediments, is it getting shallower or is it, and how quickly? So we know the processes, but the use of these radioactive isotopes, we actually put how speedy these processes are happening. Is it slow or is it quick? And we can actually say that quite accurately, and using a different time frame for different situations. So we have isotopes that look at the last 100 years, we have isotopes that look at thousands of years, we have isotopes that looks at millions of years. So it depends on the question, we have an isotope that we can use. So mangrove systems can cope with a moderate amount of sea level rise. We know that because we measure it. But combined with subsidence, it's actually a negative equation that you actually lose sediment. In the upper catchment, we can also, in the Mount Oeverhaven region, we can actually measure how much sediment is eroding from the hills into, by looking at the isotopes also in the soil. There's a whole suite of applications of nuclear techniques. And that's why we were quite unique. And we collaborated with all the nuclear organizations in the region to address all these problems. Yeah.
I heard that you work with Batan, so that's interesting. And how how Batan coming with all this type of environmental research. Okay, thank you, Prof. Henk. So maybe I would like to hear from Prof. Nandin a bit about, everything, wrap up or about the projects, maybe. Please, go.
Thank you, Budita. Assalamualaikum warahmatullahi wabarakatuh. My apologies from Henk that I am unable to stay here from the beginning because I have to be examiner for PhD student of information systems related. They develop applications to detect RAN problems. And thank you, Budita, that already moderate for this general lecture. And thanks for the student that attend for this class. It is very important because we try to update the information with the newest informations that able to be used and able to be developed in our situations. We have limited condition, limited equipment, but it doesn't mean that we are unable to do something. We are able to develop something based on our limitation, develop our collaborations, and whenever we do not have it, see that it is more than 10 years that I have collaborated with Prof. Henk. Batan unable to analyze carbon dating uses with the small amounts of samples, and I send my samples to ANSTO, to Prof. Henk, free to analyze. I have to say that because Prof. Henk tried to find out another funding to analyze it, because you see that one samples it is about $700. So just calculated how many samples I have, and then to be analyzed at ANSTO. And the last things that we have developed is Balikambang. From Balikambang, we have more than 400 sediment sample score, and Prof. Henk analyzed dating from the bottom and then until I think about 85 centimeters, and then we able to see that sediment samples from the lake, it is like diary books. And then based on that result, we able to know about the historical water supply at the end. And with magnetic suspicion, and then we also provide with the data when the eruption in the end, when the geothermal occurs in the end. And yes, this is the samples that we collected 2020 before COVID, months before COVID, and we collected, and then now we already prepare the publication and will submit in the Q1 publications. And then the other things is that with Prof. Henk, actually it is now whenever we calculate sequentially, it is 5 years with us as an adjunct professor or visiting professor. So join with us. You have to register for next Monday. We have a seminar, although it is hybrid. We will provide with certificate, but whenever you want to join offline, you have to register it, because we able to prepare anything also related to the rooms. Whenever the offline participants is high, it will be we will move to bigger rooms to accommodate all of your interested. And as Prof. Henk mentioned, mention that yesterday we went to Sayung, Demak. There are many problems in Sayung as well as in Semarang. Indeed, it is climate change that influence the sea level rises. But the land subsidence cannot be avoided because people, not only people, but also PDAM using the groundwater. So that is induce the land subsidence. So the solution is already Prof. Henk mentioned that people by the reserve try to build like pyramids, but our student KKN thematic that now they are working in Pedono also develop Istana Kerang Duma Mahe. Jadi mereka KKN the student that have a KKN thematic try to develop Istana Kerang. It is to break the wave from the ocean and protect the village, but also provide the habitat for green mussels to attach to the what should we call it, dari pralon itu diisi dengan semen. Jadi bagus sekali yang sudah dikembangkan, dan that is also another solution. So whatever you interested, you able to do something to overcome the problems. So that is why always in your introduction, whenever you write down the proposal, always state what is the problems that you would like to answer based on your research. Okay? And this is also the 6th times Cepalim have activities this year. We have four foreign experts that try to be optimized and working with Cepalim. Prof. Henk also already have the ID card of Cepalim, and he is also, of course, working with Cepalim. And yes, thank you again for all your interesting, and then research never stop. It is always another questions that have to be able to be answered. Budita, Prof. Henk, thank you. Also for the from the department that already facilitated this general lecture, and I hope it will be increase our knowledge and update, of course, our experience. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Nani. And I think this is already the time we will finish the talk today. I will give back to the Master of Ceremony to close the session. Thank you.
Okay, thank you for Prof. Henk, Ma'am Dita, and Prof. Nani for the speech and incredible material presentation about protecting water resource. Ladies and gentlemen, as we reach the end of today's workshop, I would like to extend our sincere thanks to all of you for your participation. We are also grateful to all speakers, Prof. Henk, for sharing his invaluable knowledge and insight. I apologize for any shortcoming and mistakes in my speech. See you at the next public lecture. Wassalamualaikum warahmatullahi wabarakatuh. Okay, so before we close the event, we would like to take a picture together. Maybe the one that first line can sit up because so the face will be like that. Please move forward. Okay, so I will count to 3. Ready? 1, 2, 3. Once more. 1, 2, 3. Okay, is there any more? Okay, so please raise your hand and see. Okay. 1, 2, 3. Okay. Okay, once more, guys. Okay, 1, 2, 3. Okay, thank you.